In the previous video, we were able to describe a couple different forms of lines in 3-space and then use those forms to solve problems involving lines. And in this video, we're going to do sort of the analogous thing with planes. In two-dimensional space, lines are sort of the quintessential object that's easy to study and very, very useful, particularly in calculus when you're talking about tangent lines. In three-dimensional space, lines are also very important, but so are planes. And so we need sort of a similar way, we'd like an analogous way of describing planes that pass through certain points or are parallel to certain lines, things like this. In order to find a plane, we don't actually need to know very much about it. So just in the I'm going to draw a picture here. It's really hard to draw a plane, so I'm just going to draw sort of an awkward rectangle looking thing. But imagine this to be a plane somewhere in 3-space. All right, and so here's what we're going to need in order to find the equation for this plane. The first thing we need a point on the plane. But it turns out that we only really need one point. So I'm going to call this point P. Okay? And so we'll call it x naught, y naught, z naught. Right, so this is a point in the plane. The other thing I need to know is I need to know a vector that is normal to the plane. And this is going to be called the normal vector of the plane. And so a normal vector, remember, normal just means perpendicular or orthogonal. And so I'm going to draw that in red. I'm going to draw a little right angle there. So if you think of the plane as being flat, this vector n is going to be shooting straight up. Right? And let's just give this the coordinate ABC. Right? We know it has three components. So let's give those components names as an ABC. Right? And it turns out that this is actually enough to describe the equation of the plane, this one point and a normal vector. Right? Because when I say I want to describe a plane, what that means is I want to describe all the points that live on this plane. And so if I pick another point, let me pick a point over here that's on the plane, and I'll call this point XYZ. Right? This is just an arbitrary point on my plane. The key here is that any point that I just picked, for example, that one I just drew, so any point x, y, and z on the plane has to have a certain property. Right, so it must satisfy the following. Right, so I'm going to go back to the picture, and we can think of this vector from my chosen point P on the plane to my arbitrary point x, y, z. Right? And so what is that vector? That vector, I'm just going to draw it off to the side here. That vector would be x minus x naught, y minus y naught, and z minus z naught. Okay. Well, that vector lies entirely in the plane, and so I have this normal vector n that's orthogonal to the plane, normal to the plane, and so it needs to be orthogonal to this vector x minus x naught, y minus y naught, z minus z naught. And so I have these two vectors which are orthogonal. And so if I have two vectors which are orthogonal, I know that their dot product is equal to 0. So for any point x, y, z on this plane, the point must satisfy the equation ABC dot x minus x naught, y minus y naught, z minus z naught equal to 0. Right? That vector in the plane must be orthogonal to the normal vector, and therefore the dot product of those vectors must be 0. Right? And so we can compute this dot product. So this will be a times x minus x naught plus b times y minus y naught plus c times z minus z naught. And of course, that's equal to 0. And if we wanted this to be a little cleaner, we could actually distribute the A, B, and C across each of those differences and kind of group all of the constants together. Remember that x0, y0, and z0 are fixed numbers. The x, y, and z are unknown variables. But if we were able to do that, we would get something of the form ax plus by plus cz equals d, where d, this is sort of unimportant, but just to see where this comes from, this is just ax0 plus by0 plus cz0. Right? But really the d is not that important. It just says that if we distribute all of the a, b, and c out, and we get some constant term there, we can just move that constant term to the other side. So we have ax plus by plus cz equals some constant, which we're calling d. Okay? And so here we have sort of three versions of the equation of a plane. This first one with the dot product, this is called a vector equation for obvious reasons. It is an equation and it consists of vectors. And these last two are referred to often as scalar equations. Right? And in particular, also, these are also known as the linear equations of a plane. For also obvious reasons, both of these equations are linear in x, y, and z. So let's do a quick example involving equations of a plane. So let's say we wanted to find the equation of a plane that contains the point P, which is given by coordinates -3, 1, and 5, and having a normal vector which we'll call n, which is the vector 2, -4, 1. Right? So this is probably the most straightforward kind of problem that we could do with planes. We're given the point, we're given a point, and we're given the normal vector. Right? And so what we need in order to be the equation of a plane, if we want a vector equation, we need to take this normal vector, 2, -4, 1, and take the dot product of that with the vector x minus -3, which would be x plus 3, y minus 1, and z minus 5. And we want this all to equal 0. Okay? And so we can do this dot product out. So this would be 2 times x plus 3 minus 4 times y minus 1 plus 1 times z minus 5 equals 0. Right? And this would be an equation of the plane, but if we want to get it into the nice compact form with all the constant terms on the one side, we can distribute here. So we have 2x plus 6 minus 4y plus 4 plus z minus 5 equal to 0. And so if we kick all the constants to the right side, we have the equation 2x minus 4y plus z equals, and then on the left side here we have 6 plus 4 minus 5, so we have a plus 5, so when I move that over it becomes -5. Right? So this plane that goes through the point -3, 1, and 5 and has a normal vector 2, -4, 1 can be described by the linear equation 2x minus 4y plus z equals -5. So let's do another example that's a little bit more realistic. The previous example was relatively straightforward because we were given the normal vector for the plane. And this is something that, in reality, it was something we typically don't know offhand. We actually have to compute it. So let's say we wanted to find the equation of the plane that goes through 3 points. So we want the equation of the plane containing points P, which will be -1, 2, and 2, Q, 2, -1, and 1, and R, which will be 2, 2, and 1. All right, so this is a much more realistic situation where we have a plane and we know 3 different points on it, and we want to find that equation of the plane. Right? And so just like the previous example, we want to find the normal vector. In the previous example, it was given, but here we have to compute it. Once we know the normal vector, this is very easy to compute. So in order to find the normal vector to a plane, one approach is we could find 2 different vectors in the plane. And if we have 3 points like this, we can definitely do that. But if I can find 2 vectors in the plane, then to find the normal vector, what we would need is to find a vector that's mutually orthogonal to those 2 vectors in the plane. And luckily, we know a way to find a mutually orthogonal vector to 2 vectors, and that is the cross product. Right? So in order to find 2 vectors in the plane, we can use some combination of these 2 points, or these 3 points. So for example, I can compute vector PQ. We know P is in the plane, and Q is in the plane, and so therefore this whole vector PQ is in the plane. So if I compute PQ, I get 2 minus -1, which is 3, -1 minus 2, which is -3, and 1 minus 2, which is -1. So that vector is a vector in the plane. I can also compute PR. So PR would be 2 minus -1, which is 3, 2 minus 2, which is 0, and 1 minus 2, which is -1. Right? Now I computed PQ and PR. You could have also computed PQ and QR, or PR and QR, or RP and QR. It really doesn't matter. The idea is we just need to find 2 different vectors that are in the plane, and any vector that goes from one of these 3 points to the other will suffice. So now to find the normal vector, which we call n, we can take the cross product of these 2 vectors, PQ and PR, or if you found other vectors in the plane, the cross product of those 2 vectors. Right? So we will go back, we'll use a determinant here to compute this cross product. All right, and so for the I term, it looks like we have 3 minus 0, so we get 3i. For the j term, it looks like we get -3 minus -3. So that's -3 plus 3, so we get 0j. I'm just going to write 0j, even though, of course, that doesn't mean anything. And for the k, it looks like we get 0 minus -9, so we have 9k. Right? And so this is the vector 3, 0, 9. Okay. And so to find our equation of the plane, we take our normal vector, 3, 0, 9, that we just computed with the cross product, and we take the dot product of that with the vector, and we have to pick a point. And we have 3 choices of a point here. So we could do, I'll use P, so I'll have x plus 1, y minus 2, z minus 2. And we'll want that to be 0. And so we multiply this out, so we have 3 times x plus 1 plus 0 times y minus 2. Obviously that term will disappear. Plus 9 times z minus 2 equals 0. And so when we work this out, we get 3x plus 3 plus 9z minus 18. And so we get the equation 3x plus 9z equals 15. All right, so we have this equation. Now, before moving on, it's worth mentioning here that this is not a unique form for this equation of a plane. This is just an equation. It describes all points on the plane. So we look at all the points that satisfy this equation. And notice that I could do a lot of different things with this equation. For example, I see the coefficients here are 3, 9, and 15. I could divide each by 3 and get a simpler equation with smaller numbers. And that would have the same solution set as this given equation, right? And in fact, if we go through this process, we actually made a number of choices that affected this final answer. I chose to pick my two vectors in the plane to be PQ and PR. As I mentioned at the time, we could have picked any vectors between these 3 points. We could have picked QR and RP, for example. And if we did that, when we compute the cross product, we probably would not get 309, but rather some scalar multiple of 309. We know it would have the same direction, but it probably wouldn't have the same length. The other choice I made is once I had my vectors PQ and PR, I chose to compute the cross product as PQ cross PR. I could have computed PR cross PQ, and that would have given me the negative of the cross product that I actually obtained. I would have ended up with -3, 0, -9. And so that would have caused a slightly different linear equation at the very end of this problem. And so the thing to keep in mind here is if you do this problem with different vectors, you might not get 3x plus 9z equals 15. You might get this equation multiplied on both sides by -1, or by 3, or by -3, or by 5, or some other constant. So it's always important to remember that these versions of these equations for planes are just equations, and they're not unique. Okay. So I do have a few more examples I want to do with planes, but I'm going to do those in a subsequent video.